Good morning, everyone. Today we will discuss inorganic chemistry topic metal carbonyls from Pradeep's book 8.14 section metal carbonyls. Most transition metals form complexes with a wide variety of uncharged molecules like carbon monoxide, substituted phosphanes, and unsaturated or aromatic hydrocarbons. In majority of these, the metal atom is either in zero oxidation state or another low oxidation state, generally plus 1 or minus 1. We have already explained pi bonding between the transition metal atom and the olefinic or acetylenic complexes in the previous section. Compounds in which carbon monoxide is attached through a metal carbon bond to a transition metal atom in a low oxidation state are called metal carbonyls. The first metal carbonyl compound, nickel tetracarbonyl, was prepared in 1890 by Almond in England. It is used in commercial process for the refining of nickel. Mond happens to be the founder of the English company ICI, Empirical Chemical Industries. He is also remembered for his passion of arts, the carbonyls of other metals with cobalt, molybdenum, chromium, tungsten, rhenium, and iridium were subsequently prepared. In order to understand the bonding in metal carbonyls, let us concentrate on the structure of carbon monoxide. Carbon monoxide has a total of 10 electrons in the outer orbitals. The structure of carbon monoxide can be expressed as a resonance hybrid. The most important contribution comes from the valence bond structure with a triple bond between carbon and oxygen. Metal plus carbon double bond oxygen gives metal negative single bond carbon positive double bond oxygen in resonance with metal double bond carbon double bond oxygen. Preparation of metal carbonyls. Metal carbonyls can be prepared by several methods. Some of methods of preparation are described below. First method is direct method, i.e. metal plus carbon monoxide. Nickel and iron carbonyls can be prepared by the direct reaction of finely divided metals with the stream of carbon monoxide. Nickel plus 4 carbon monoxide at 25 degrees Celsius temperature and 1 bar pressure, nickel tetracarbonyl is formed. Iron plus 5 carbon monoxide at 150 degrees Celsius temperature and 100 bar pressure gives FeCO3 का whole twice. These compounds must be handled carefully as they are very toxic. Reaction number second, reduction reaction. Metal salt plus reducing agent plus carbon monoxide. Mononuclear and polynuclear metal carbonyls are prepared by a process known as reductive carbonylation, in which a transition metal in a high oxidation state is reduced to zero oxidation state in presence of carbon monoxide. Following reactions: CrCl3 plus Al plus Co in presence of AlCl3 gives CrCO4 plus AlCl3. Reaction number 2, 2COCO3 plus 2H2 plus 8CO at 170 degrees Celsius temperature gives CO twice bracket CO whole 8 plus 2 CO2 plus 2 H2O. Reaction number third, Re2O7 plus 17 CO at 300 degrees Celsius temperature and 300 atmosphere pressure gives Re2CO whole 10 plus 7 CO2. WCl6 plus 3Zn plus CO gives WCO6 plus 3ZnCl2. 6 RuACAC thrice plus 9 H2O plus 24 CO at 150 degrees Celsius gives 2 Ru thrice brackets CO का whole 12 plus 18 ACACH. VCl3 plus 4Na in presence of CO diglycol methyl ether. It gives Na diglycol methyl ether whole twice positive plus VCO whole 6 negative plus 3 NaCl. Then they further react in presence of H3PO4 gives VCO6 plus H2. OSO4 plus 9CO at 250 degrees Celsius temperature and 350 atmosphere pressure gives OSCO whole thrice plus 4CO2. Third reaction is photolysis or thermolysis. Higher metal carbonyls can be easily prepared by photolysis or thermolysis of lower metal carbonyls. For example, 2FeCO whole 5 in presence of sunlight CH3COOH whole gives Fe2CO whole 9 plus CO. Second reaction 3Fe2CO9 in at 386 Kelvin temperature gives Fe3CO whole 12 plus 15 CO. Next reaction CO2 CO whole 8 in presence of heat gives CO4 CO whole 12 plus 4 CO. Fourth reaction miscellaneous method. A number of methods other than mentioned above can be used for the synthesis of metal carbonyls. For example, base hydrolysis of FeCO5 yields the hydrido complex carbonyls. FeCO whole 5 plus 2OH negative gives a complex HFeCO whole 4 negative plus HCO3 negative. 3HFeCO4 negative plus 3MnO2 gives Fe3CO whole 12 plus 3OH plus MnO. The binuclear carbonyls Fe2CO whole 5 is an organometallic compound, whereas the trinuclear Fe3CO12 is a shining grey colored crystalline solid. Iron pentacarbonyl FeCO whole 5 is sometimes used as a source of carbon monoxide in the preparation of some other metal carbonyls. For example, tungsten hexacarbonyl is prepared by reacting WCl4 with iron pentacarbonyl using hydrogen as a reducing agent under high temperature and pressure. WCO whole 6 plus 3FeCO whole 5 in the presence of ether H2 gives WCO whole 6 plus 3FeCl2 plus 9CO. The metal carbonyls are all crystalline solids with the exceptions of FeCO5, RuCO whole 5, OSCO whole 5 and NiCO4, which are ligands. They melt or decompose at low temperatures and are either insoluble in water. Example NiCO whole 4 or decomposes by water FeCO whole 5. Reaction of metal carbonyls. Metal carbonyls present in table 8.6 are air and moisture sensitive. Metal carbonyls undergo a variety of chemical reactions. Some of the important reactions they undergo are presented below. First, displacement reaction. One of the most important reactions metal carbonyls undergo is the displacement reaction, in which one or more of the carbon monoxide ligands may be displaced in contact with electron donors such as pyridine, phosphines, isocyanides, etc. The rule of thumb is that one CO is replaced by one electron pair donor. As a result, six electron donors like benzene is displaced by three CO ligands. Some of the important displacement reactions are FeCO whole 5 plus PH3P gives FeCO whole 4 PPH3 plus CO. Next, FeCO whole 5 plus 2PH3P gives FeCO3 PPH3 whole twice plus 2CO. Next, MOCO whole 6 plus PY gives MOCO whole 5 PY plus CO. Next, MOCO whole 5 PY plus PY gives MOCO whole 4 PY whole twice plus CO. Next, CrCO whole 6 plus C6H6 gives CrCO whole thrice Ca6H6 plus 3CO. Next, FeCO whole 5 plus 2C5H6 gives 2N power 5 C5H5 FeCO whole twice further whole twice plus 2CO. Next, CO2 CO whole 8 plus RC double bond CR gives CO2 CO whole 6 RC double bond CR plus 2CO. Next, MOCO whole 6 plus C5H5Na gives NaN whole 5 C5H5MO CO whole thrice plus 3CO. Second reaction, anionic or cationic carbonyl complexes. These are three important methods for the conversion of metal carbonyls into anionic and cationic carbonyl complexes. There are three important methods for the conversion of metal carbonyls into the corresponding anions. First, metal carbonyls react with bases to give carbonylate ion. FeCO whole 5 plus OH negative gives FeCO whole 4 2 negative charge plus H positive plus CO2. Next, Fe2CO whole 9 in presence of KOH in MEOH at Et4Ni gives Et4N whole twice Fe2CO whole 8 plus CO. The reaction is believed to proceed by nucleophilic attack of OH negative on the carbon atom of carbonyl group followed by the electron transfer of the metal atom and formation of carbon dioxide, which is converted into carbonate as CO whole 4 Fe single bond C triple bond O in presence of OH negative gives CO4 Fe single bond C double bond O in is further same C single bond OH. gives FeCO4 2 negative plus H positive plus CO2. Second reaction, reduction of metal carbonyls with alkali metal amalgams or borohydride produce carbonylate ions. For example, CO2 CO whole 8 in presence of NaHgTHF gives 2 Na positive CO whole 4 negative. Mn2CO10 NaHg in THF gives 2 Na MnCO whole 5. Next, CrCO whole 5 in presence of NaNH3 gives Na2CrCO whole 5. Next, CrCO whole 6 in presence of NaBH4 THF gives NaHCr2CO whole 10. Next, CrCO6 in presence of NaBH4 NH3 gives Na2Cr2CO whole 13. Next, Re2CO3 in presence of NaBH4 THF gives Na2Re4CO whole 15. Third, many substituted carbonyl anions can be obtained by displacement of carbon monoxide from a metal carbonyl. For example, Me4Ni plus MoCO whole 6 gives Me4N MoCO whole 5I plus CO. Next, MoCO whole 6 plus NaB3H8 gives NaMoCO whole 5 B3H8 plus CO. Next, FeCO whole 5 plus MnCO whole 5 negative in presence of sunlight gives FeMnCO whole 9 negative plus CO. Fourth reaction, cationic carbonyl complexes may be obtained in the form of complex halides by the action of carbon monoxide and a Lewis acid such as anhydrous AlCl3 or BF3. For example, MnCO whole 5Cl plus CO plus AlCl3 gives MnCO whole 6 positive AlCl4 negative. Cationic carbonyl complexes can also be obtained by protonation of carbonyls in strong acids as FeCO whole 5 reacts with HCl in BCl3 gives FeHCO whole 5 positive BCl4 negative. Third, formation of carbonyl halides. The action of chlorine, bromine, or iodine on some carbonyls give carbonyl halides. For example, Mn2CO whole 10 plus Br2 gives 2MnCO whole 5 Br. Next reaction, MnCO whole 5 Br in equilibrium at 120 degrees Celsius temperature in presence of carbon monoxide gives MnCO whole 4 Br whole complex twice. Next reaction, FeCO whole 5 plus I2 gives FeCO whole 4 I2 plus CO. Next reaction, 2MoCO whole 6 plus 2Cl2 gives MoCO whole 4 Cl2 further whole complex twice plus 4CO. Carbonyl halides can also be prepared by the interaction of metal halide and carbon monoxide. For example, RuCl3 in presence of COMOH 65 degrees Celsius temperature and 10 atmosphere pressure gives RuCO thrice Cl2 further whole complex twice. Next reaction RuCl3 into 3H2O gives RuCO whole twice Cl2 further whole twice in presence of carbon monoxide at 100 degrees Celsius temperature and 1 bar pressure. Fourth reaction formation of metal metal bonds. The metal metal bonds can be formed by powerful reducing agent or by simple elimination reactions. MnCO whole 5Br plus LiMnCO whole 5 gives MnCO whole 10 plus LiBr. 2MoCO whole 6 plus 2NaBH4 gives Na2MO2CO whole 10. Bonding in metal carbonyls. Carbon monoxide is a natural gaseous molecule and is considered to be a very weak base. However, it forms a number of stable molecular compounds with transition metals. The high stability of metal carbon bond in metal carbonyls is due to the multiple nature of carbon single bond CO bond. In order to understand the bonding in metal carbonyls, let us look first at the structure of carbon monoxide. It has a total of 10 electrons in its outer orbital and its structure can be shown to possess a lone pair of electrons both on oxygen as well as on carbon. Carbon triple bond oxygen having a lone pair on both carbon and oxygen. If you recall, classical ligands such as NH3, ethylene amine are strong Lewis bases and form bond to metal ion such as Ag positive or Cu2 positive ion Lewis acids by donating its lone pair of electrons. These ligands are capable of reacting with metal ion where these are in high positive oxidation states. Accordingly, NH3, AgNH3 or Cu NH3 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 whole 2 positive. Carbon monoxide, on the other hand, is a very weak Lewis base, but it's surprisingly capable of forming stable molecular compounds with transition metals in zero or low oxidation state, generally +1 or -1. For example, CO combines with acid metal at room temperature to give a compound NiCO whole 4 where nickel is in zero oxidation state. Carbon monoxide has a triple bond between carbon and oxygen with lone pair of electrons on both carbon and oxygen as shown. Although we can formulate the bonding in metal carbonyls in terms of resonance hydride, resonance hybrid of structures 1 and 2. Molecular orbital picture gives a more detailed and graphic picture of carbon monoxide. Metal plus carbon triple bond oxygen having a lone pair on both carbon and oxygen gives M single bond C free radical on carbon triple bond oxygen having one lone pair in resonance with M double bond C free radical on carbon double bond oxygen having two lone pair. Molecular orbital picture takes into consideration the multiple nature of carbon metal single bond carbon monoxide. First, it forms a sigma bond by donation of one pair of electrons on the carbon end of carbon monoxide into a suitably directed empty orbital on the metal, as shown in figure 18.8. Secondly, there is a formation of a pi bond by back donation from the filled metal d orbitals into the anti-bonding orbitals of carbon monoxide, as shown in figure 8.18b. This compound bonding mechanism is synergic. This is because drift of metal electrons into CO orbital will make CO more negative and hence increase its basicity via sigma orbital of carbon. On the other hand, drift of electrons to the metal makes CO more positive and thereby increases its ability to accept sigma electrons. In brief, sigma bond formation strengthens sigma pi bonding and vice versa. The ability of the ligand carbon monoxide to accept electron back donation from the filled metal orbital into the empty pi bonding orbital is called pi acidity. Carbon monoxide is therefore pi acceptor ligand in the Lewis sense. The metal carbonyls are thus considered complexes of pi acid ligands. Evidence for multiple bonding in metal carbonyls. We have noticed that the bonding in metal carbonyl has two components. One is the formation of metal carbon sigma bond, and the second is the stimulus formation of carbon metal pi bond. Evidence in favor of this multiple nature of metal carbon monoxide bond comes from the study of bond length and vibrational spectra. In formation of sigma metal carbon bond forward bonding, the negative charge is developed on metal atom. However, the metal atom cannot accommodate negative charge. This developed negative charge is pushed back. This can be pushed back into anti-bonding orbitals of carbon monoxide by forming a metal carbon pi bond. Back bonding, as the extent of back donation from metal carbon oxide increases, the metal carbon bond becomes stronger. However, this strengthening of the metal carbon bond is at the expense of bonding in carbon triple bond oxygen. It means as the metal carbon back bonding increases, the metal carbon becomes shorter. The carbon double bond oxygen becomes weaker, and consequently carbon triple bond oxygen becomes longer. The bond length in pure carbon monoxide is 1.18 angstrom, whereas in metal carbonyls the bond length of carbon monoxide molecule increases to 1.15 angstrom. This increase is justified as a decrease in the bond order increases the bond length. However, this increase in length is very small, which is approximately equal to 0.022 angstrom. In fact, very little information can be obtained from the carbon monoxide bond length. This is because in the range of bond order 2 to 3, carbon monoxide bond length is relatively insensitive to bond order as shown in figure 88.19a. However, metal carbon bond distances compared to metal oxygen bond distances are fairly sensitive in the range of bond order 1 to one can see that the sensitivity is zero point 0.3 to zero point 0.4 angstrom per unit of bond order as shown in figure 8.19b. Thus, good evidence of multiple bonding can be expected from metal carbon bond lengths. However, this approach cannot be used extensively in the estimation of length of metal carbon single bond because zero valent metals do not form each other bonds. Vibrational spectra of metal carbonyls. Infrared spectroscopy is a variable tool for explaining bonding in metal carbonyls. It provides information regarding bond orders, metal carbon, and carbon oxygen bonds in metal carbonyls. A decrease in the carbon oxygen bond order or force constant can be estimated by studying the carbon monoxide stretching in the infrared spectroscopy. Force constant K is measured of the bond strength and is given by the relation V is equal to 1 by 2 pi under root K by mu. Equation 8.1, whereas mu is the reduced mass of the bonded atoms with mass m1 and m2 and is given by mu is equal to m1 into m2 by m1 plus m2. Equation 8.2. The larger the force constant, the stronger is the bond and higher the vibrational frequency. A triple bond has a higher force constant than a double bond, which in turn has a higher frequency than a single bond. In other words, a triple bond has a higher frequency or wave number than a double bond. For example, the wave number in case of carbon bond is 2200 centimeter inverse. In case of carbon double bond carbon is 1650 centimeter inverse, while in case of carbon single bond carbon it is 1000 centimeter inverse. Similarly, the wave number in carbon double bond oxygen is higher than carbon double bond oxygen. Free carbon triple bond oxygen shows infrared stretching frequency at 2143 centimeter inverse. There is a considerable decrease in stretching frequency of carbon monoxide in metal carbonyls. Depending upon the way carbon monoxide is bonded to the transition metal, the stretching frequency of carbon monoxide varies. Carbon monoxide can be bonded to the transition metal in three different ways as shown below. Terminal, doubly bridging, triply bridging. In it can act as a terminal ligand as shown in A, bridging ligand as shown in B, and triply bridging ligand as shown in 3. Depending upon the types of bonding, the stretching frequency of carbon oxygen changes as shown in table 8.7. If carbon is carbon oxygen free bond, then its frequency is 2143 centimeter inverse. If it is the terminal carbon, then its frequency is 2125 to 1900. If the carbon oxygen bond is in bridging, then its frequency is 1850 to 1700. If carbon oxygen bond is in triple bridging, then its frequency lies between 1700 to 1600. Free carbon monoxide has a stretching frequency at 214 centimeter inverse. Terminal carbon monoxide group in neutral metal carbonyl molecules are found in the range of 2125 to 1900 centimeter inverse, showing clearly the reduction in carbon triple bond oxygen bond order. Moreover, when changes are made that should increase the metal carbon back bonding, the carbon monoxide frequencies are shifted to even lower values. For example, if some carbon monoxide groups are replaced by ligands with low or negligible back bonding ability, those carbon monoxide groups that are left must accept more d pi electrons from the metal to prevent the accumulation of negative charge on the metal atom. This will result in the decrease in the bond strength of carbon monoxide, which is marked by lowering in carbon oxygen stretching frequency. As an example, CrCO whole 6 has a stretching frequency at 2000 centimeter inverse due to terminal carbonyl pair. Three of the carbon monoxide groups are replaced by an amine group that have essentially no ability to back accept, as in chromium CO whole thrice diethylene, where di in double bond NH2 CH2 CH2 whole twice NH. The stretching frequency due to CO group should be lowered to greater extent. In fact, the stretching frequency in case of CrCO whole thrice diene appear at 1900 and 1760 centimeter inverse. The oxidation state of metal also have an effect on the carbon oxygen stretching frequency in metal carbonyls. In case of negatively charged carbonylate anions such as CO whole 4 negative or FeCO whole 4 2 negative, the negative charge must be taken from the metal atom and be pushed into the anti-bonding orbitals of carbon monoxide. As a result, there must be more pi back donation from the metal to the anti-bonding pi star orbitals of carbon monoxide. This would lead to further weakening of CO bond and hence reduce CO stretching frequency. The higher the negative charge, the greater should be the lowering in CO stretching frequency. For example, when we move from CrCO whole 6 to the isoelectric VCO whole 6 negative with more negative charge, the frequency shifts to 1860 centimeter inverse, corresponding to the frequency found at 2000 centimeter inverse in CrCO whole 6. On the other hand, the effect of replacing positive charge on the metal in metal carbonyls will have the reverse effect. With positive charge on the metal, its pi back bonding ability is reduced relative to neutral molecule, hence lowering of carbon monoxide stretching frequency will be minimum in cationic metal carbonyls. For example, CO stretching frequency in MnCO whole 6 whole positive appears at 2090 centimeter inverse, whereas its neutral isoelectric molecule has CO stretching frequency at 2000 centimeter inverse. Structure of metal carbonyls. We have already studied that carbon monoxide can bond to transition metals in three ways. Let us first of all discuss the structure of mononuclear metal carbonyls. Mononuclear metal carbonyls have all terminal CO groups. They have simple geometries, namely tetrahedral, trigonal, bipyramidal, and octahedral. For example, hexacarbonyl is such as VCO whole 6, MCO whole 6, M double bond Cr, MO and W have regular octahedral geometry. Nickel tetracarbonyl has a tetrahedron geometry, whereas pentacarbonyl of iron, osmium, and ruthenium has trigonal bipyramidal geometry. The shapes of mononuclear carbonyls are shown in figure 8.21. Binuclear carbonyls. Some of the important binuclear carbonyls are shown below. These carbonyls show metal-metal and bridge bonding. In case of dimanganese decacarbonyl, there is only metal-metal bonding. No bridging carbonyls are there, as shown in figure 8.22. Each metal atom has an octahedral arrangement of CO groups. The structure of Mn2CO whole 10 is shown in figure 8.22. Some of the binuclear carbonyls also have bridging in addition to metal-metal bonding. The important examples are that of Fe2CO whole 9, OS2CO whole 9, and CO2CO whole 8, which are shown in figure 8.23. In case of Fe2O CO whole 9, there are three bridging CO groups placed symmetrically around the Fe single bond Fe bond, whereas in case of OS2 CO whole 9, there is only one bridging CO group, which with each osmium having four terminal CO groups around it. Figure 8.23b. The infrared spectral studies help show the presence of bridging CO group in the metal carbonyls. The CO stretching frequency of bridging group is lower than the terminal CO group. For example, the terminal CO group in CO2 CO whole 8 absorbed in the region 2000 to 2100 centimeter inverse, whereas bridging CO group have bonds in the range of 1880 to 1860 centimeter inverse. We have already noticed that the terminal CO groups appear in the region 1850 to 2150 centimeter inverse, and the frequencies for bridging group appear in the range of 1750 to 1850 centimeter inverse. Typically, bridging CO group appear at still lower frequency in the range 1620 to 1730 centimeter inverse in neutral carbonyls. Let us summarize the CO stretching frequency values in carbonyls. Tetra nuclear carbonyls. The important tetranuclear carbonyls possesses the formula M for CO whole 12 where M double bond CORH and IR. They have tetrahedral arrangement of four metal atoms as shown in figure 8.24. In case of CO4 CO whole 12 and RH4 CO whole 12, three triangular faces consist of terminal MCO whole twice group with one bridging CO group along each edge. The fourth triangular face is occupied by an MCO whole thrice group in figure 8.24a. In case of IR4CO whole 12, there is no bridging and the structure is symmetrical with 4 IRCO whole thrice terminal units in a regular tetrahedron. Figure 8.24b. CO2CO whole 8 binuclear cobalt carbonyl CO2CO whole 8 exhibits two structures which are in equilibrium with each other. In the solid state, there are two bridging carbonyl groups and each cobalt atom is bonded to three terminal CO groups. The two CO groups are bonded together by metal bond in solution. CO2CO whole 6 has CO single bond CO bond and each cobalt atom is bonded to four terminal carbon monoxide groups as shown in figure 8.24a. Although the bridging CO group may be written in the kinematic form, yet it rarely display any ketonic properties. The bonding in bridging carbonyl groups may be regarded as two electron 3 centered overlap. It is important to note that bridging occurs in conjugation with metal bond. The carbon monoxide bridges in the absence of metal bond are not stable. Trinuclear carbonyl stability of the CO bridges depends upon the size of the metal atom. Large-sized metal atoms tends to destabilize CO bridges and show greater preference for non-bridged structure. In other words, relative stability of non-bridged structure increases as the size increases along a group. For example, Fe2CO whole twice has three bridging carbon monoxide groups, whereas the bigger osmium has one bridging carbon monoxide group in OS2CO whole 9. Similarly, Fe3CO whole twice has two bridging, whereas the corresponding Ru3CO whole 12 and OS3CO whole 12 have none. Thank you.